This is a short tutorial on covalent bonding and Lewis structures. We'll start off with a review of ionic. Now, how do atoms form bonds? How do they form ionic or covalent bonds? Well, let's start off with ionic bonding. Ionic bonding is seen generally between metals and nonmetals, or between metallic ions and polyatomic anions. For example, sodium ions and chloride ions get together to form sodium chloride, NaCl. And the positive ion, the cation, attracts the negative ion, the anion, by electrostatic attraction. Calcium nitrate is forming also in the same way. The calcium ion, Ca2+, attracts two nitrate ions, NO3-. Because that has a -1 charge, you need two of them to neutralize the calcium 2+ charge. And this is a simple diagram of what that looks like. The calcium ion in the middle and the nitrate ions on either side. In the crystal, of course, there would be calcium ions over here and over here and over here, and then nitrate ions as well. All of them having that formula CaNO3 taken twice. What about covalent bonds? What atoms form covalent bonds? Well, that's those that don't have enough difference in electronegativity so that one of them, the more electronegative ion, can steal electrons from the other, like sodium loses electrons to the chlorine to form sodium ions and chloride ions. That doesn't happen in a covalent bond. To attain a low-energy octet, therefore, with that low-energy noble gas configuration, the atoms that aren't very different in electronegativity from each other have to share electron pairs. So, for instance, we have fluorine, oxygen, nitrogen, sulfur, carbon and chlorine, and bromine and boron and hydrogen. When these bond with each other, not with metals, they're going to share electron pairs. They are, of course, non-metals. What's really happening? Well, atomic orbitals, we know, are shown by mathematical functions, probability functions that give us what we called mosquito graphs. Then when atoms share, they're going to overlap their atomic orbitals to share the electrons in those orbitals. Now, by computer, we can add up the basic psi functions, and then, once we have added them, we can square the values of these functions to get a probability of finding the electrons, and that's something that we can graph. We graph them to find out the areas of maximum and minimum densities. Let's do that for hydrogen. This is a hydrogen molecule. You see the position of the nuclei here at a certain distance from each other, and you see the mosquito graph, the electron densities, where the two electrons of the hydrogen atoms are very, very dense between the two nuclei and not so dense on the other sides. Another look. Consider the electron configuration in the box diagram for hydrogen. 1s1. If we put two of these hydrogens together using a box diagram, we see the 1s1 of one hydrogen and the 1s1 of the other hydrogen. If we bring them close together, we can form a bonding orbital with these electrons now paired together, with different spins, of course. Now, there's also an antibonding orbital formed because orbitals don't just disappear, but you can talk about that in AP chemistry. This electron pairing has a lower energy than the two individual atomic orbitals, and that's why it forms. Now we can also do what's called Lewis structures. You may remember the electron dot method of showing electron configurations around an atom. You just show the valence electrons of those atoms. For example, with hydrogen, that's one electron as a dot. We can show electron dot structures for molecules as well. These are named Lewis structures after Dr. G.N. Lewis, an early 20th century chemist. This shows two electrons being shared by two hydrogen atoms. The pair of electrons holds the molecules together because they're attracted to both nuclei. This is a covalent bond using a Lewis diagram. The two dots symbolize the two electrons in the electron cloud you saw the mosquito graph a couple of slides ago. And the electron clouds are holding the nuclei together. How do we draw Lewis structures for molecules? Well, we write the symbol for the element, starting with the least electronegative element in the center. Except hydrogen. Hydrogen can never be in the center because it can only bond once. We then add the valence electrons as dots surrounding the symbol in a clockwise direction. We do the same for all the other atoms and link them to the central atom using electron pairs to fill up their outer shell. And if you have extra electrons, you make a double bond between the central atom and one or more of the others. Let's do an example. Beryllium and hydrogen. Write the symbol for the element. Beryllium is in the center because hydrogen can't be in the center. We add the valence electrons as dots, one on this side and one on the other. And we bring in the hydrogen with its electron on either side, and we get beryllium dihydride, BeH2. Now carbon dioxide. Again, we write carbon in the center. It's the least electronegative of carbon and oxygen. We add the valence electrons as dots, surrounding the symbol in a clockwise direction. Then we add the oxygen with each one has 6 valence electrons, and so we will draw a covalent bond between the carbon and the oxygen atoms. We have extra electrons, as you can see, 2 on the carbon and 1 on each oxygen, and so we make a double bond between the carbon and its 2 oxygens. And we see now we have 8 electrons around the carbon and 8 electrons around each of the oxygen atoms. We have the octet. We then clean it up by moving the unbonded electrons around so the repulsive effect is minimized, and the AP Chemistry examiners like you to show bonding pairs as lines rather than as the 2 dots. So because these are bonding orbitals, you show the electron pairs as lines, not as 2 dots. These, however, are lone pairs. The lone pairs are still shown as dots. Now let's do boron trihydride. We start with the central atom, since hydrogen cannot be at the center, and it has 3 electrons. The hydrogens bring in each 1 electron. Boron trihydride has what we call an incomplete octet. One of the boron orbitals is empty. Do you think it's an s orbital or a p orbital on that second energy level? If you think about it, it would be the last orbital filled, and that would be the 2p orbital. And here we can change the bonding pairs to lines, as the AP examiners prefer. Now let's do methane. You do this by yourself and then turn the video back on to see how you did. Here's the carbon, hydrogen. Again, there are 4. There are the electron pairs, and here are the lines. We'll see that the geometry here is tetrahedral. The electron pairs are going to arrange themselves 3-dimensionally around the carbon, and the hydrogens, of course, will be with those electron pairs. And so this is a 3-dimensional thing. The boron trihydride would be planar, and then the carbon dioxide would be linear. There's much more that we can do with Lewis structures, and you will do, but that will wait until you get into AP Chemistry.